Good morning, dear students. Welcome to this session on Unit 5 of your syllabus, JNTUK, Structural Analysis 2, under the bunch of displacement methods. We are now to discuss kani's method. Okay. Till last session, it was moment distribution method that is being completed. So in this session onwards, we will take up kani's method, okay, which is another distribution method. So let's go and see what we are uh, need to discuss in this session. So the complete unit 5 of your syllabus consists of analysis of continuous beams, including settlement of supports. You have much of varieties in this. The analysis of continuous beams with fixed ends is a case. The another one is like hinge end, maybe one option, or overhanging can have continuous beams can have overhanging portion. Similarly, the sinking of supports. And when it comes to frames, two-dimensional frames, we are going to discuss the frames without sway and also with sway. Okay, so this is the topic that is need to be considered. So let us see what exactly is Kani's method, how it is being developed, how it is going to help us beyond this Hardy-Cross method or moment distribution method. So under the bunch of displacement methods, the earliest method or the first method that we have been discussing is slope deflection method that is being dealt in structural analysis 1 in your previous semester of your JNTUK syllabus. Now, in this structural analysis 2, we have discussed moment distribution method, which is now a little bit what we can say the slope deflection method is made easy by the iterative procedure by Hardy-Cross, and the name of his method is moment distribution method. And now one more distribution method is being developed by a German engineer uh, who is Gasper Kani. So he is the one who developed this method, the Gasper Kani. He is the one who developed this method, which is again very similar to this moment distribution, but uh, where the Hardy-Cross used the joint total moment of the joint to be distributed, whereas Gasper Kani worked on rotation contributions of the ends of a member that we will see in the procedure. So this is very much useful for the multi-story frames. The particularly its use is in this multi-story frames. And what advantage you have this now over and above the moment distribution method? If you see that if any mistake is committed anywhere in the distribution process, in any of the cycles, if you have committed a mistake, finally it converges to the required solution. That is the greatest advantage of this method. You don't need to worry about that some value in a particular cycle is posted wrongly, finally your solution converges to the required value, but it takes little longer. In number of cycles may increase, but finally you will get the required solution. So sign convention we will follow as it is, like previous one. So all clockwise moments are positive, clockwise rotations are also positive. Okay, so theta clockwise positive and moment clockwise positive. Okay, so this is just very similar to the earlier moment distribution method, but the difference is there we have used the total joint moment is to be distributed to the members, whereas here rotation contributions are to be calculated. Okay, so that's why this name of this method, the other name of this kani's method is rotation contribution method. Okay, so that's how it is to be. No, the other name that I was telling, rotation contribution method, but it is more popularly known as kani's method. Okay, right. Whereas the moment distribution method is not no, popular with Hardy Cross name method Hardy Cross. It is still popular with moment distribution method name. Okay, whereas Kani's method, which is a rotation contribution method, is popular with the name Kani's method. Okay, which means the advantage of that method with multi-story frames to be designed manually. Okay, so let us see what exactly we do in this method. So the figure that you see here, I have taken a member AB, right? Is an intimate member of a beam or a frame, whatever it is. Just no relative displacements at the ends, which means I'm not taking any settlements like sinking effect. Okay, right. So MAB, MBA are the final end moments that are being required for us. Okay, right. So MAB, I mean, we shall understand this way. Moment at A of any intermediate member, let us say this is being cut from a continuous beam. So I'll just extend this member and show a cut here. Okay. So as this A is a continuous end, also B is a continuous support. So A is a continuous support, B is also continuous support. So moment at A is a combination of three values. So M, A, B. How moment at A is going to be developed. So moment at A will be developed because of loads when there are no rotations. Means what? You arrest the rotation A and B, take only loads, given loads on the member. Okay. Now you calculate moments. That what we call them fixed end moments. Okay, right. So the loads will cause moment at A. Okay, we are talking about only NDA. We'll come back to B also. So loads will cause some moment at A. Also, rotation of NDA. So now remove the loads. Apply only rotation of A. Okay, means release A. Try rotate this A, because rotation is possible for A. You see, this is a hinge support. So because of this rotation, you will have some moment at A, that we call it as M dash AB. Okay. Similarly, the rotation of the end B also creates some moment. Because of the B rotation, there will be some moment at A. Okay. So that is what is called M dash BA. Okay. So this is the reason for moment at A. How moment is developed at A. Loads will cause moment at A. Also, the rotation of that particular end will cause some moment. Means if there is rotation, there should be a moment. Even if the far end is rotated, this A will get some moment from the far end rotation. So it is combination of three values. So fixed end moments, nothing but moments from loads. Moment due to rotation at A, moment due to rotation at B. So if you add these three values, you will get end moment at A. Similarly, B also. Okay. So this is a reason for moment at any continuous support. Okay. So it consists of three values. One is fixed end moments, nothing but moment from loads when you don't allow any rotation, and moment due to only NDA rotation, moment due to B rotation. Okay, right. So that is what is being shown in the diagram. Okay, so the this is the actual figure that is being taken from any of the structure. So first arrest the rotations. You make theta A 0, theta B 0. Then the given loads will cause moments at A and B. That is what we are writing, MFAB and MFBA. Okay. You may even take the notation writing F like this. We are following this one. So like this. And now take rotation of A only, arrest B. So what we call is M dash AB. Okay. So 2 times M dash AB I'm writing, because half value is going to be taken to far end. So instead of writing this as M dash AB and this as M dash AB divided by 2, to get a to avoid that divide by 2, I'm taking this as 2 times. So half is nothing but M dash AB. Okay. And you know the value, the moment required, or moment developed at that point is 4A by L into theta A. Okay. Similarly, next case, end B rotation also will cause moment. That is, I'm writing is 2 times M dash BA to avoid divide by 2 here. So half will carry here, that is M dash BA. Again, this is 4ei by theta b by L is the moment required to rotate this end by theta b. Okay. And now, if you try write what is total moment at A, MFAB plus 2 times M dash AB plus M dash BA. So that is written here. MFAB 2 times M dash AB M dash BA. So fixed end moment at A. This is rotation contribution at A, 2 times rotation contribution, nothing but near end contribution. A is the end that we are considering, that's why it is called near end. This is B, which is far end. From A, this B is far end. Similarly, moment at B, if you want, so take fixed end moment at B and 2 times near end contribution, near end rotation contribution, and far end rotation contribution. Right? So, how you are writing that? The symbolic notation is M dash AB, M dash BA are called rotation contributions. Means what? As they are rotating, they are going to develop the moment. So that is what is rotation, contribution from rotation. So final end moment in the form of writing, if you write it as a sentence, fixed end moment plus 2 times near end rotation contribution plus far end rotation contribution. So you see that we are talking about rotation contributions. That's why the name is rotation contribution method, nothing but kani's method. Okay. So final end moment that you are calculating here is fixed end moment plus 2 times near end rotation contribution plus far end rotation contribution. Okay. Whereas in case of moment distribution, what you have done, so you have made a table. So something like this, some A, B, okay, so A, B, like this. So you had fixed end moments written here, so some minus 10, plus 10, like this. And now carryover moments from far ends, all are here from different cycles, cycle 1, cycle 2, cycle 3, cycle 4. All those far end, what you call carryover moments. So all the carryover moments you have added, finally you got the value. So there, in case of moment distribution method, it was simply MAB is equal to fixed end moment MFAB plus sum of carryover moments from different number of cycles. I is 1 to n. Okay, n is number of cycles. So if you have 4 cycles, all 4 carryover moments you are going to add, isn't it? That's what it is. Okay, so that's how we have calculated the end moments in moment distribution method. So there is no point of rotation contribution involved in this one, but inherently it is there in fixed end moments itself. Okay. So now carryovers, balancing, all that is the process there. But whereas here you have to find these rotation contribution values, then only you will get final end moment. Okay. So this is uh, the uh, the background information, the required information for what exactly is Kani's method. Okay, so let us derive the rotation factor which is required for the procedure and also the formula for rotation contribution to calculate rotation contribution in the next session. Okay, so we'll take up this in the next session. So finally, if you just recall, the kani's method is another distribution procedure based on slope deflection equations only. So same, the slope deflection method that is being developed, fundamental method, is being simplified by so many scientists. So among them, the popular ones are moment distribution method by Hardy-Cross, and now rotation contribution method, nothing but Kani's method by Gaspar Kani. Okay, so the basic ideology is slope deflection method only, but how do you simplify to overcome the difficulties of slope deflection method? That is what they are, then the different scientists have been concentrated. Okay, so this is how it is. So finally, the end moment, as per Kani's method, end moment is consisting of three values: fixed end moment, moment due to rotation at A, moment due to rotation at B. Okay, so that is given in the form of equation, which is MAB is MFAB plus 2 times M dash AB plus M dash BA. It is for end A, similarly for end B, which means final end moment is equal to fixed end moment plus 2 times near end rotation contribution plus far end rotation contribution. Okay, thank you.